Okay, today I want to discuss two things. First, I want to finish this chapter on Lattice QCD, and then come back to this, to what's already in the lecture notes. And the next topic there is spontaneous symmetry breaking. So, before doing that, the usual questions. Are there any things you would like to discuss from, for example, from the topic of yesterday?
From the lecture notes, when you talk about the Heisenberg magnet, I don't know, but like maybe you should discuss.
I will come to that anyway. Yes.
Yeah.
Yes. Okay. Okay. Otherwise, then I would continue with Lattice QCD. So last time I showed you some results, and basically I ended up with a formula which one can calculate by brute force on the lattice. So let me write this down again, that it's clear what I'm talking about. So suppose one had operators which depend on fermion fields and times an operator which depends on the gluon fields, and one wants to calculate the expectation value of that. Then in the end, the integral or the multiple integral one has to calculate. So this is what I wrote down last time as a last expression, is a multidimensional integral over all gluon fields. Then this operator which depends on gluon fields in the way one is interested in that. Then a new operator, which I also will write down again in a moment. Then the determinant of a matrix, basically the Dirac matrix. And finally an exponent where the Euclidean QCD action, but the part where one only has the gluons in, shows up, and this also depends on the field. And it depends on these variables which in the end one wants to have very big values, which is this beta and the three-dimensional volume. And then this matrix M here was given by basically the Dirac operator with a gauge covariant derivative and the Quark masses. And this derivative is a derivative with respect to x. And what else do we have? And this T of M, which is a function of this Dirac operator, was given by the operator which depends Quark fields. And there one needs some derivative with respect to sources. And an exponent where one has minus eta bar, and basically the scalar product over all lattice sides of this matrix with the source terms. And in the end one puts eta to 0, eta bar to 0 after one has performed these derivatives here. Okay, so for example, if one has a quark-antiquark field which one wants to study, in other words, a meson operator, And if I'm interested, say, in the mass of the lowest lying meson with these quantum numbers, I would put psi bar psi at some position and another operator psi bar psi at a second position. And then this O2 would contain exactly these four operators, but I can create these operators as derivatives of this exponential here. And this then brings down basically powers of this m. M to the -1 probably. Yep. To the power of -1. And the non-trivial thing is that this object here contains, in this gauge covariant derivative, also the gluon field. If it would not contain the gluon field, this would be just the ordinary Dirac operator, and this would be, well, the inverse of the Dirac operator, which is basically a free fermion propagator. But then this object here is basically a fermion propagator in the presence of arbitrary many gluon configurations. Okay, so this one calculates numerically, and well, at least this is the ideal thing that one does that, and then there are some remaining challenges. And essentially I want to discuss two of them. There are, of course, technical challenges which are completely typical for such a numerical evaluation, and that is, and these are things which I will not write down. Of course, here, these cannot be infinitely many integrals. These are integrals over the gauge configurations on the different lattice points. Actually, this is still a little bit oversimplifying. These gauge fields in the end do not live on the lattice points, but actually on the connections between lattice points. This makes the whole thing also in the discretized version gauge invariant. This I skip here because this is not so important, and essentially this is an aspect which is solved. This is not a challenge. But anyway, so there is only a finite number of fields here, well, corresponding to this finite number of lattice points. And of course, as always in any numerical evaluation of things which are supposed to give in the end a continuum limit, one has to make sure that one has enough lattice points to simulate the continuum limit. And this is basically done by doing calculations for different number of lattice points, and one then figures out whether one observes a specific scaling with the number of lattice points. One can basically show if results are close to the continuum limit, how would they scale if the number of lattice points is changed. And this scaling one has to analyze, and if it turns out that one does not see this scaling, this basically means one is far away from the continuum limit. If one observed this scaling, this is not a proof that one is close to the continuum limit, but at least it is a consistency check. Okay, so this is something which one anyway has to do with anything which is discrete, and every numerical calculations are discrete. So in that sense, this is not a particular challenge for Lattice QCD, but in general for numerical simulations of a continuum theory. But now comes particular things, which are typical for QCD, and not for arbitrary, well, and not for numerical physics sake. Okay, I want to bring up two things here, and one thing which I already addressed last time is some hadrons are very, very light. In practice, this concerns pions. So let me phrase that in the form that they might be so light that they do not fit on the lattice. Fit on the lattice means their de Broglie wavelength, which is 1 over the mass. Well, if this is bigger than the whole lattice, I obviously do not really simulate this state. So they might be larger than the lattice size. So this is if the mass of, now let me stick to the pions, no sorry, if the de Broglie wavelength 1 over the mass of the pion, if this is bigger than, well, the total size of the lattice is the number of lattice sides times the distance between the lattice sides. So this is n times A with n number of lattice sides. Well, in one direction. This is not now the total number in all 4 directions, in the direction of beta and in the 3 spatial directions, but so this is the number of lattice sides in one dimension, or in one direction. And A is the distance between 2 lattice points. 2 lattice, well, 2 lattice sides are always right. So if the lattice is so small that this is happening, and of course this is a question of computing power. The more lattice sites I have, I mean the more I have to calculate. And well, reaching the physical pion masses is at the moment is at the edge of what's numerically possible. So there are lattice calculations which can do that. They typically then study more simpler observables, and there are a lot of lattice calculations which are also useful already nowadays, but still they operate with somewhat too large. Well, they operate with smaller sites, and then if one wants to do that, of course one still wants to have the lightest state on the lattice, but for this one has to basically, one cannot go to the physical input parameters. One cannot go in practice to the average of up and down quark mass, which is so small as it should be physically. So if one cannot have a large enough number of for n, so if this is the case, then one has to stick to a too large value of MQ, which is 1 average up-down quark mass. With too large, I mean larger than physically, larger than in the physical world. Well, the reason why this is the limitation and not a combination of this and a strange quark mass and a coupling constant, the reason for that is that the pion mass actually scales with exactly this quantity. And why this is so is something we will learn later in these lectures. When we understand that the pions are actually Goldstone bosons and of chirosymmetry, which means they would be massless if the up and down quark mass were zero, and if they are not zero, then they obtain a mass. So later in the lectures, we will see that the pion mass actually scales linearly with the quark mass, which means if I choose a value of MQ which is bigger than physically, bigger than in the physical world, then my pion mass would also be bigger, and then this would fit on the lattice. Okay, and then what I, in addition, of course, should tell you is, if nonetheless these masses are not very big, well, bigger than physically possible, but not on the level of, say, 1 GeV or so, then actually the masses of the other particles are not influenced so much by this wrong up-down quark mass. So it's a complicated reasoning. The pions are mostly influenced by that, and this is a necessity if the physical pions would not fit on the lattice. But the other particles are not so much influenced by that. Otherwise, I mean, one would simulate something which one does not have under control at all. Okay. So why could that be useful nonetheless? The issue is that one can look at, again, this chiral limit. Remember, this is something we have discussed before. We have an approximate chiral symmetry, and in the presence of this approximate chiral symmetry, one can actually figure out how do observables scale with a finite but small up-down quark mass. Now suppose my lattice is big enough that now I have to become a little bit qualitative, that I'm nearly here, but not quite. Then it is suggestive that I can use my results from, well, what happens when I have a zero quark mass, do an expansion around this limit in powers of the quark mass, try to figure out how qualitatively my observables change when I change the quark mass in a range where it's still small, and then I can try to describe my lattice results, which have a too large quark mass, but maybe it's still small enough that one can think about this expansion in powers of the quark mass. So basically one matches two regions here. There is one region which one can simulate. One can start with a small number of n and a large value of this, such that still my unphysical pion fits on the lattice. Then I try to go to larger and larger lattices and to smaller and smaller quark masses, and try to figure out how do my observables behave when I change the quark mass. So this is a thing where I come from large quark masses and try to go to smaller and smaller ones by going to larger lattices such that it's allowed to go to smaller quark masses. This is the numerical aspect. And there is an analytical aspect where one does something which is called chiral perturbation theory, and this is something we come to at the well, after we discussed spontaneous symmetry breaking, there one starts with 0 quark masses and expands results in powers of quark masses. So this is something where one starts at 0 quark masses and tries to reach a region with sufficiently large quark masses, and with lattice QCD one comes the other way. Now if the lattice calculations are, well, still had the problem that this n is too small, these two regions would not overlap, and there is no use in doing that. But at the moment it seems that at least for the best lattice calculations, well, I'll say the second best, the best lattice calculations already have reached pion masses, but as I said, they concentrate on specific simpler quantities. So in that sense, for the second best lattice calculations, it seems that one is already in a region of small enough quark masses that there is an overlap between their calculations and what one is doing in lattice, what is doing in an expansion in powers of quark masses. Okay. For small enough, and again this is something which in practice one has to explore what does small enough mean. For small enough pion masses, pion or quark masses, one can use chiral perturbation theory. And again, this is something which will come later in the lectures. To determine how specific observables change when changing m pi or q, which is equivalent because of this relation here. So then the issue is to check whether really what one calculates here with chiral perturbation theory matches to the m pi behavior of observables as extracted from lattice QCD. If there is an overlap between basically this calculation, which works good for large values of m pi, and then one tries to come to a region where one has smaller ones, and this here, which is an expansion in powers of basically mq, and in that sense in powers of m pi. Okay, second problem. Now this is something where basically one would say, okay, then we wait for some other years, and then one is also numerically there to simulate pion masses. Of course, you know, we physicists, we don't want to wait if we can already extract from the present calculation something. But for sure, nowadays there are still a lot of discussions how well one can match these calculations, and if one has better calculations, one definitely can make more precise statements about that. So this is work in progress, which is again for sure also driven by the improvements in the numerical calculations. The second aspect is the fermion determinant. Which is this determinant of m, which shows up here. And I already argued at the end of the last session that in a determinant one always correlates basically all lattice sides with all lattice sides. So this determinant, again, one obtains that by basically looking at this object here for all values of x and x prime. And x and x prime are basically characterized by lattice sides. So this is a matrix, and in a determinant I always calculate, well, for each contribution to a determinant I need basically in each row and column one entry, which means I need to multiply things which live at very, very different sides. So this here correlates information at different lattice sides. Well, of course, this can only correlate things which are physically correlated. If they are not physically correlated, basically these contributions would not then depend on the details of what I'm doing there. However, well, we have physical effects which work over large distances. We have very light pions. So pions do correlate. I mean, one would not see them as pions, but one would see in the simulations to which extent are different lattice sides indeed correlated. And if the quark masses are small, actually they are. And this makes the calculation of this determinant numerically very expensive. So in particular, for small mq, which basically means small m pi. Because of this, in the old days, there was an approximation. Nowadays one does not use that so frequently anymore. And this approximation was just to neglect this determinant here. Do all the rest, but neglect this here. So this is called quenched. Lattice QCD, which is just neglect this determinant. Let me give you an idea what one is doing there. Well, let me first write it down. This amounts to actually neglect closed fermion loops. Now I talk about basically Feynman diagrams in spite of the fact that, well, if one writes what one calculates in Lattice QCD in terms of Feynman diagrams, one has infinitely many Feynman diagrams. So in that sense, just displaying some is not a good approximation. However, that one gets a feeling what's going on there, Feynman diagrams are nonetheless useful. So one example. So let me look at the meson correlator. A meson correlator is that I put a quark anti-quark field somewhere. So let me display this in this way. I have a quark and an anti-quark, which is my meson. And I have, well, another meson correlator at a different point, and again I tear them basically apart and study how this expectation value changes as a function of the distance, and from this distance I extract the mass of this thing. So this is now meant to be read in coordinate space in the sense that there is something here at this space point, and there is something here at another space point, which is in a sense the anti-meson. And in principle what one can imagine here is that there are very, very many gluons exchanged. For example, like this. So these guys here are quark lines, and these guys here are gluons. Basically, these interactions here, so maybe let me first start. So basically, these interactions between quarks and gluons, this comes about from the fact that in this M here is a coupling to gluons. And actually this operator here creates exactly these two quark lines. This is what essentially one obtains by calculating these derivatives. One basically gets these quark propagators in the presence of gluons. Well, in a sense here they are. These are propagators in the presence of, in that sense, where gluons couple. And basically this action here, well, on the one hand side tells how it looks like when you now connect two of these vertices, and it also creates additional interactions like I have displayed here, these three gluon interactions. This comes from this gluon action. So such diagrams, and I think you can imagine I could draw now arbitrary many lines. So all such diagrams which you can consider here, starting with one gluon line and very, very many, up to infinitely many, all this is included by calculating this average here with this and this. And without this here. This here creates something in addition. So this here is included in a quenched calculation. Whereas, so now let me start with the same thing, and now I draw some, yep.
What do you mean by n plus?
Well, I mean, if I would start with a pi plus here, this would be a pi minus. Because, I mean, you can read this as this here creates a state, creates a meson, and this here creates an antimeson or destroys a meson. Maybe I should rather say this is a meson field and an antimeson field. And the idea is that I start with vacuum, then my operator can of course also destroy states, but if there is nothing, the destruction part does not do anything, then this guy when evaluated with a vacuum state, just creates a meson. And this guy in principle can then create another meson, but then when I sandwich that with a vacuum state, this would be 0, and it can annihilate the meson which I've created before. I could add this here, creates meson, and this here annihilates meson. Or you can also read it the other way around. So now let me draw a second diagram. I could imagine to have something like this. So to have a closed fermion loop in here. And the rest is the same. And I could imagine also having now infinitely many gluons in the same way as here, but I just want to show you now here the most simplest diagram, because this is actually already not included in a quench calculation. You know, the message is, if I tell you something is included, I want to tell you how complicated things are actually included. That's why I have a complicated diagram here. When I tell you what's not included, I want to show you very simple things which are already not included. There is not the point. When it's not included, it's not the making a point that this is very complicated. Okay. Okay, so this here is not included. And one can ask, of course, how significant is that? And it turns out that for a lot of states, I have shown you an old 10 years old lattice calculation in this quenched approximation, and the results were, well, quantitatively concerning masses of hadrons, they were quantitatively not exactly where they were supposed to be, but I mean the ordering was right, they were nearly there. So for a lot of states, when one determines the mass, this is not so critical to leave that out. But in practice, one has to check that. This is the issue. Maybe one does not know right from the start how critical that is. One thing which is worth noting here is, now let me draw this slightly differently. In between here, I have a quark anti-quark state. And in between here, I also have a quark anti-quark state. So actually this here has a contribution where one started with a meson, but intermediately one has a two-meson state. If mesons are unstable, and most of the mesons we know of are unstable, they decay into other states, then this here, such a diagram would contribute to this decay. So actually in the quenched approximation, the finite lifetime of the mesons is for sure wrong. This is not in. And the question is, how significant is that, for example, for the mass of a meson? Again, it seems that for the particles one typically studies, this is not so critical. The fact that they have a finite lifetime has not much influence on what their mass actually is. But such effects are in here. Especially finite. Of a resonance is tied to tied to such diagrams. No, let me give a name to these guys. A. So it's not that one obtains the correct physics from a quench calculation, but some things might come out quite okay. Still, this is something one wanted to overcome, and basically for most of calculations nowadays it is overcome. I have shown you some glue ball calculations, and as far as I know, this was a quench calculation for glue ball masses, these masses of particles which are supposed to consist only out of gluons, and experimentally we do not have any definite proof that they exist, but okay, from quenched lattice calculations one has obtained a glue ball spectrum. These glue ball calculations are not at a level yet that one thinks that one has completely overcome all complications which come from including this determinant. So an unquenched glue ball calculation with reasonable results, that's still something we're waiting for. Now let me come to one final issue. Of course, nowadays one includes this determinant, and then one might think, okay, now everything is fine. Whatever is supposed to be in this numerical calculation is in, but actually there are still some remaining problems when including this here. And this has to do with the symmetries of QCD again. So if one includes the fermion determinant, again, this is something you want to do, of course. So this is what one calls unquenching. One actually picks up another problem, and this goes under the name of the fermion doubling problem. The fermion doubling problem essentially means if one analyzes how many degrees of freedom, how many fermions essentially, one has on the lattice, it turns out that one, if one would simulate one continuum fermion, it turns out that one actually does not have on the lattice one fermion, but basically if one has 4 dimensions, or if one has d dimensions, one has 2 to the power of d fermions. Now these additional fermions in principle decouple if one goes to the continuum limit. However, I mean, if you think about that numerically, if you have too many degrees of freedom, and for any finite grid distance you have too many degrees of freedom, it's hard to believe that then suddenly, when you could approach the continuum limit, which you cannot do anyway, you can only come close to that, that suddenly the number of degrees of freedom goes back to its original value. This is just not happening. At least it's not happening automatically. Therefore, one has to do something to it. One has to get rid of these fermions which one has on the lattice and which are too many. So let me first give you an idea how they actually come about. Well, on a lattice, which implies that one is not in a continuum limit, one has discrete lattice sides. One has too many fermion degrees of freedom. And basically one can see that when studying a dispersion relation. Do I have another blackboard? Yes. What I discuss with you now briefly is basically a fermion without interactions, because if one switches on the interaction with the gluons, this number counting does not change. So this is a problem which basically appears already if one tries to simulate a free fermion theory on the lattice, which is not very spectacular. I mean, these are non-interacting states then. But of course, formally one can do that. And let me assume, because after all we are interested in light fermions, let me assume that for a moment we neglect the masses. Well then, in the continuum, one has the following dispersion relation. So I plot now a wave number or a momentum, and I plot the corresponding energy. And so how would it look like? What's the energy of a free particle without mass?
It's linear. Linear to the...
Yes, so omega is just P. Okay, so this is how it looks like in the continuum. And from that, basically, one reads off, if, in a sense, if you want, from the zero here and how it starts, one can already read off the whole information. The dispersion relation I read off basically here from the slope. Now, on a lattice, any idea how it looks like on a lattice? So this is now a question to any of you who have ever had a solid state physics lecture. All the others need not answer that. Who never had a solid state physics lecture? In a solid state you have a Brillouin zone. Ever heard of that? And basically, all the physics is in this zone, and then you have the next Brillouin zone, which just has the same information as the one before. If one has discretized information, you cannot have arbitrary high momenta. They are limited by this Brillouin zone. And actually there, one has a periodicity. For the fermions, it's slightly different. One actually has an anti-periodicity there. But the issue is that the dispersion relation looks like that, and here is pi over a if a is the lattice distance. Okay, now basically one reads off a degree of freedom, one reads off a dispersion relation close to where the energy is zero. There one tries to read off what is the relation between energy and momentum. Okay, that's a good strategy here. Well, why one reads it off here? Well, you see, if A goes to 0, this moves to infinity, and then the only thing which is relevant is this start here, which looks like this. If A goes to infinity, I should come from here to here. Okay? If A goes to 0, sorry. If the discretization goes to 0, the Brillouin zone goes to infinity. So this part here is what one is interested in concerning the continuum limit. And in a continuum limit then, if I'm close enough here, I read off the same dispersion relation as here. So this here is the relevant part in the continuum limit. However, I have a second 0 here. I have here a dispersion relation which just is opposite. In a sense, it just has an opposite phase. I can actually translate that to fermions which just have an opposite phase in their wave function. Well, this is something which in the naive continuum limit disappears. This is so far out that I don't need to bother about that. But for every finite box, for every finite lattice distance, this is not at infinity. This is somewhere. And in a sense, this here is a second fermion. And this picture I can draw basically in any direction. And therefore for d dimensions I have 2 to the power of d additional fermions. Now all this, I mean what I showed you here, one could also of course draw the same thing for bosons. I have not told you why this is a problem now for fermions and not for bosons. Actually, now comes an additional aspect in which becomes even more technical, and therefore I will not go into detail now. All this becomes especially an issue for massless states. So I talk about the massless limit here, the chiral limit, what actually we are interested in. We are interested in something close to the chiral limit. And in the chiral limit, there is, in addition to this chiral symmetry, there is an anomaly, which is something we will discuss later on in these lectures. This anomaly essentially is responsible for the fact that this here is a physical issue. This anomaly, the chiral anomaly, does only show up for fermions, it does not show up for bosons. And actually this is now a little bit of twisted logic. This chiral anomaly exists. We need that to describe the correct physics. I will come to that later in these lectures. This chiral anomaly exists, we need it, but actually for every finite grid distance, there is no chiral anomaly. These guys here exactly cancel the chiral anomaly caused by these guys. And this is happening for every finite grid distance. However, for every finite grid distance is what I can calculate. I can go to small distances, but I cannot go to 0 distance. And if something is present for every finite distance, and if I then extrapolate to the continuum limit, I end up with a wrong result. So actually, this theory does not have a chiral anomaly, but one wants to have one to get the physics right. And therefore, this is an issue only for fermions and not for bosons. So the second fermion always means for every A non-equal 0, and this always cancels the physical. So physical in the sense that in the continuum limit it should be there. And therefore, in a sense, one has the wrong continuum limit. Just because one does not obtain the continuum limit by formally putting A to 0, but one has to approach it. And if it's always wrong, it cannot suddenly become right. Now there are 3 ways out of that. And all come with some special names, and at least I want, even if you have, this is hard to understand and I have not given you any details, but at least I want that you pick up the following names which basically tell how one deals with that problem. And I want to discuss basically the advantages and disadvantages of that. The first way out are staggered fermions. Basically, the logic with staggered fermions is if one has too many fermions and basically if their properties are more or less the same on the lattice, just that they act oppositely to each other, but otherwise they are basically the same, which is basically, if you turn this around here, this slope, except for the sign, is exactly the same as here. If this is so, it was suggested, well, this comes from the determinant, so why not taking a root of the determinant? As many roots such that one only has in the end then find the number of fermions one wants to have. So in other words, if one has two fermions instead of one takes the square root of this determinant, and then the square root basically eliminates 1 degree of freedom. For sure in a free theory this is okay because this decouples. Whether this fully decouples in an interacting theory, I mean, one can argue with that, concerning different chiralities of these fermions. So staggered fermions is take roots of this determinant instead of really calculating this object, one first takes a root here and then calculates that. This sounds like a very, very bold approximation. It's not obvious that this gives something reasonable, but this was tried and it turns out that for a lot of calculations, comparing now this method to the other methods, which I will discuss after the break, it turns out that there was numerically not so much difference. The purists would say this is something, if one changes by hand the thing which one wants to calculate, obviously this is a different theory from what one had before. However, numerically it turns out that so far no one has found any significant differences. So one argues again here with practical experience, not so much with a completely first principle derivation of that. So far, no significant differences in results. But from a principal point of view, this is, well, maybe not so appealing. The calculations which I've shown you for, well, these very good calculations for the lowest hadron masses, nucleon, sigma, omega, cascade, kaon, pion, and so on, if I'm not mistaken, they are with these staggered fermions. So there is a grain of salt in these calculations. There are two other ways out of that, but for this I would first like to make a break. So then I suggest we reconvene at 2:30. Okay. So now there. So actually, I don't know how I labeled that. This was number 1, right? With the staggered.
Yes.
Yeah.
And so I'm still discussing how to deal with this fermion determinant. And the second option is something which is, well, nicer from a principal point of view. And these are the so-called Wilson fermions. And what one is doing there is one basically gives a large mass to these additional unphysical fermions. One gives a mass to them such that when the continuum limit, when one goes to the continuum limit, this mass basically becomes bigger and bigger, and then they are less and less relevant. So basically, one does not use the, well, I have not told you how one discretizes these whole things, but one does not use a naive discretization, but adds terms which would disappear in the continuum limit, but for every finite value of A they are there, and they give a big mass to this additional unphysical fermion, such that when something has a very big mass, it cannot influence the rest very much, basically because it's not moving and not taking part in any interactions. So give a big mass to the fermion doublers. And these are additional terms. Basically additional terms in a discretized action. Okay, this is from the point of view of how to get rid of these fermion doublers. This is satisfying, because in the continuum limit this would not contribute, so it has the right continuum limit. Whereas if you take a root of a determinant, of course, in the continuum limit, still this root would persist. However, there is one unpleasant thing about that. If you give a big mass to something which is related to light particles, and the light particles should show some symmetry, the chirosymmetry, then by this effect here you basically break by hand the chirosymmetry. So the disadvantage is that it breaks chirosymmetry explicitly. Now, from a principal point of view, one can argue, well, of course, this chirosymmetry breaking becomes less and less severe when one goes to smaller and smaller distances, because it's tuned like that the effect disappears in the continuum limit. However, from a practical point of view, it's somewhat unsatisfying if you simulate a theory where then in your simulation a symmetry is broken, then you simulate it a little bit better, the symmetry is still broken, well, it's broken to a not so much extent, but whatever you do, the symmetry is always to some extent broken. And I mean, you need a lot of trust in your continuum extrapolation when you always have something where the symmetry is broken and you want to extrapolate to something where then hopefully the symmetry is not broken. So there is still something one feels uneasy with. Okay, so this is the disadvantage. Now, the interesting thing is, if one tries to protect the chirosymmetry on the lattice, then there is actually a no-go theorem which tells you either, but if you want to have if you want to have a chirosymmetry on the lattice, if you want to have our chirosymmetry on the lattice with its left and right-handed fermions, there is a no-go theorem which tells you either you have to break chirosymmetry explicitly, what's done by the Wilson fermions, or you have to do the trick of the staggered fermions by artificially, by hand, taking out some degrees of freedom. You cannot have, well, say non-staggered and protecting chirosymmetry. So that's a no-go theorem. In that sense, it seems as one has to choose either to break it by hand and hope that in the continuum limit chirosymmetry is recovered, or use the staggered formalism. Well, as with many no-go theorems, there is a way around that. And there are several ways how to do that, but one are the Wilson-Ginzburg fermions. I think that's the way to write them. Yep. The no-go theorem applies to the chirosymmetry as it is defined for the continuum limit. It applies to the chirosymmetry basically, well, as I defined it to you, one introduces this left and right-handed projectors, projects out left and right-handed components of this four-component Dirac spinor, decomposes everything in left and right-handedness, and then, well, the chirosymmetry would mean that these interactions decouple, that there is no interaction between left-handed directly and right-handed, except by gluon exchange. This here is much more clever. This here circumvents the no-go theorem in the following way. One defines an exact symmetry on the lattice, which looks different from the continuum limit chirosymmetry. But one has on the lattice an exact symmetry for every grid distance. And in the continuum limit, this symmetry reduces to the one wants to have. So one does never have a symmetry, an explicit symmetry breaking like with the Wilson fermions, but the symmetry explicitly looks different than it looks in the continuum limit. But one has an exact symmetry for every lattice site. This is much more satisfying. So one defines a lattice chirosymmetry that reduces to the ordinary one in the continuum limit. So in that way, one basically one inherits the advantage of the Wilson fermions, but at the same time one always has an exact chirosymmetry. However, then one has to find a discretized action such that this symmetry is exactly satisfied, and this is actually complicated to do that, so there is no free lunch. So one has to find such that the new symmetry is exact. Basically, it amounts to find a gamma 5 which reduces to the gamma, or this left and right-handed projectors which reduce to the ordinary left and right-handed projectors in the continuum limit. Well, this find here put it that way. Finding this action, however, is actually, it's not that, well, at some day one person has to be clever enough to write that down, but actually finding that is something one has to do numerically. This is a nonlinear action, and one has to numerically determine the coefficients of all, basically, well, of all terms which one writes down in this action. So this is a numerical process, and this is, in a sense, the cleanest way how to do that, but at the moment the computers are not there that this is numerically feasible for most calculations one is after. So it's a question of computing power. So in the future, this will be more and more feasible how to do that. And essentially, this is, I believe this is the way to go, because the other ways of dealing with this fermion doubling problem are essentially unsatisfying. Manipulating by hand the action by taking roots of the determinant is a manipulation by hand, and breaking chirosymmetry for every simulation with the hope that this is irrelevant when one approaches the continuum limit, because formally this breaking goes to zero. This is also unsatisfying. So on the long run, this is the way to go, and the question is how to do this numerically. Either in a more clever way than today, or well, maybe by finding better starting actions and then optimizing that, or by going to bigger computers. Okay. I know this was a tough chapter, but what I wanted is that you see some lattice results, but not only see them, but at least get an idea how this is done. And I definitely wanted that you see these keywords, how lattice calculations are characterized. And if it's only for that, at least when you are somewhere and hear a talk about Lattice QCD, in the end you can ask a clever question. You can ask, for example, so which fermions do you use in your calculation? This always sounds very clever. And for sure, typically this is not said by the speaker, but if you ask him, he will tell you whether he's using Steggart or Wilson and so on. So if you want to show up by a clever question, these are the keywords you need there. Of course, I assume that then you want to know that, and not only ask that because you want to show up, but okay. Practical suggestions in doing research. Okay.